Okay, so now we're on to my favorite method, NMR spectroscopy. So NMR spectroscopy, you may recall, elucidates, or what does it measure? You may recall that it measures connectivity, or tells us how atoms are connected with respect to each other. Now, the way that it does that is really interesting, and we're going to get a lot of information out of it. So first of all, it does it with the location of the signal, and then it does it with and then it tells us that with respect to the size of the signal, and then it gives us information by the form of the signal. Okay, so these three things. Let's look at these three things one at a time. So first of all, here's a classic NMR spectrum. It's the NMR spectrum of. Let me get my red marker out. It's the NMR spectrum. Just a minute. Why is that black? It's the NMR spectrum. Watch this, of paraxylene. Okay, so paraxylene. It's got a benzene ring on it, and it's got a methyl group over here and a methyl group over here. Now there are two signals present, and this is consistent with paraxylene because we've got look at these. We've got let me get that in green. We've got these 6 hydrogens are all identical, right? And these 4 are identical. So, and they're identical, right? So these, you've got 4, and then these, all right? So they show up in 2 different places. Now, if you see an sp3 hybridized carbon with a hydrogen on it, it's going to show up roughly in that range right there, right? And sure enough, that's what we see right here. It shows up just a little bit over 2.3, I guess, and it that's the red hydrogens. Okay, those are they right there. Now, the benzene, that's hydrogens on a benzene ring. This is classic, 6.5 to 8. Okay, watch for that. This is a major red flag for you when you're analyzing spectra. You see something down here, it's a hydrogen. It's almost guaranteed a hydrogen on a benzene ring. Okay, so the location of the signal tells us a great deal about about how atoms are connected. Can you see that? This tells us that we've got atoms connected to a benzene ring, and we should put the formula of hydrazine up there, right? So it looks like there's 8 carbons, so it's C8H10. Is that right? C8H10, 6 here. Yeah, and I think that's it, right? So if I told you I had some C8H10, and you know, I have some C8H10, and we know that because we burned it, because our combustion analysis told us that we had 8 carbons of well, combustion analysis with maybe some colligative property too. We found we had C8H10, right? If I told you that, then I said, what do we have? Well, you would say, well, gosh, I have no idea, right? There's so many ways those atoms can be bonded to each other. And that's what NMR does for us. It gives us insight about this. So if I said I have C8H10, and then I gave you this spectrum, you go, oh, wow, look at that. You've got a signal between 6.5 and 8. You have a benzene ring in there. So I go, all right, well, I know I must have this, right? How's that? Write that a little bit neater. I'd go, well, I know I must have a benzene ring, right? So there's 6 of them. And so I've got C2. I haven't said how many hydrogens are on there, right? But I know I've got 2 carbons left to assign, right? So can you see how this is helpful? All right, hopefully so. So the location of the signal is going to give us a lot of information. Let's talk now about the size of the signal. All right, so the size of the signal is going to tell us how many hydrogens are represented by that signal. So if I've got a benzene ring, I know I got a benzene ring because I got a signal down here between 6.5 and 8. Look at that signal right there. Very telltale. So I got a benzene ring in there. I have 4 hydrogens. Aha, okay. So this is one possibility, right? Another possibility is, man, I'm messy. 1, 2, 3, 4, right? But at least I know I'm way down the road with respect to how much information I yet don't know, right? So these are other things, right? So, and they must be carbons, I guess, right? Because that's the only way we can. Anyway, can you see what we've got here? Since this signal it's got a 4 next to it. Oftentimes, when you're given an NMR spectrum, the size of these signals will be integrated for you, right? This one's not, so I put them on there. But usually they are. So if we had a 4 here, we go, well, there's 4 hydrogens on a benzene ring. And we have 6 down here. And we'd say, well, there's 4 hydrogens or 6 hydrogens that are not on a benzene ring, right? Okay, so the size of the signal tells us how many hydrogens are are represented by that signal there. So again, the size will be given to you normally, and that tells you how many hydrogens are there. They're represented by that signal. I know I'm repeating myself, but it's so simple when you get it. All right. So what's the next thing we get? So the form of the signal. So this is complicated. All right. The form of the signal. And now in that previous, let me go back one slide. This form is just a single line, right? You see that? It's really hard to get any information out of it. It's just a line. But that's not always going to be the case. It turns out that neighbors split the signal. So the signal we looked at previously was not split. But if you have neighbors, we'll split the signal. What do you mean by that, Dr. Kopic? Well, here's what I mean. Look at this. You see this hydrogen right here? Let me get orange. So you see this hydrogen? A neighbor is a hydrogen that's bonded to the carbon that's next to the carbon that this hydrogen is bonded to, right? So if I'm interested in the neighbor of this hydrogen right here, then what I got to do is I got to go down to that carbon, go to another carbon, right? And I would say, all right, all the hydrogens bonded to this carbon here. So if this is carbon 1, this is carbon 2, all the hydrogens bonded to carbon 2 are the neighbors, okay? So the green hydrogens are the red hydrogen's neighbor. Do you see that? Neighbors. For my grammar. Subject-verb agreement. Okay? So the green hydrogens are the red hydrogen's neighbors. The black hydrogens are not. Okay? So the temptation sometimes is to go, well, a neighbor must be somebody who's close. Well, here's a close hydrogen, right? But he's not neighbor. No, not a neighbor. He's not a neighbor because he's in the same house, really, if you can think of it like that. All right. So now that we've got that, let's look at this a little more carefully. Now, if we say neighbors split the signal, let's look at this. What does the split do? Well, the split is the number of neighbors plus 1. Okay. And by that I mean that if we've got, so let's look at this hydrogen right here. If we've got, let's look what the next slide says. Okay, how many neighbors does hydrogen have? How many neighbors? Say it out loud. Hydrogen has here 2 neighbors, right? Because these greens count as neighbors because we go, there's the one it's bonded to. We got to go over 1. Now every hydrogen bonded to carbon 2 is a neighbor, so it's got 2 neighbors. Now what is n plus 1? N plus 1 is equal to 3, of course, right? So what kind of a signal are we expecting with that guy right there? Well, there's like say let's say a Gaussian curve of some kind, right? So if this is a signal that's not split, if it's split in 3, it's going to look like that. It's going to be like a Gaussian curve, but 3 curves underneath it, right? So that would be a triplet. This is a singlet, and this is a triplet, okay? So you are expecting, when you look at this compound, you're expecting these hydrogens right here to be in a triplet, right? Now what about the next one? What about the number of neighbors? This is 3, right? Or 2. What about the number of neighbors that green has? How many neighbors does green have? All right, so let's call this carbon 1. And so we go over to carbon 2 and we go, oh, look, there's 3 neighbors. Aha, there's 3 more. So we're expecting, look at this, the number of neighbors that these guys have, the greens have, is actually 6. So n plus 1 is equal to 7. So we're expecting 1, 2, 3, 4, 5, 6, 7. Okay, a 7-plet. And obviously there's going to have so many, the splitting is so much, it's going to be a little difficult to even tell what that is. Okay, let's look at the example. Let's look at the spectrum. This is propane here. Let's look at the spectrum of propane. All right, so we're looking for a triplet. How do you spell triplet? And we're looking for a 7-plet. I'm sure there's a better name. Heptaplet, I guess, right? We're looking for a 7-plet. Do you see anything on there that might be a triplet? Yes, this is a triplet right here. Aha. And here's a 7-plet, okay? The next question is, let's go back. Remember we had the location, the size, and the form, right? Those were the three things. So the location, we said it's going to be in this area right here if it's sp3 hybridized, and they both are, so that doesn't really tell us much. But we said the size. Now, if this is propane, let me get red on here for. Okay, and then green for. Okay, this is the 7-plet because it's got 6 neighbors, right? N is equal to 6, n plus 1 is equal to 7, and so that signal, the size is going to be relatively 2, right? And what's the size of the red? The size of the red, there's 6 there, right? Can you see that? Give me a nice 6 here. 6. And me a nice 6. Come on, I can do it. Watch this. 6. Beautiful. All right, so tell me, does this look like this could be a 6 compared to that 2? Yes, it does. Definitely. This totally makes sense, right? And let me go further and say that the form, right, we already said this. This has got 7 neighbors. We're expecting, or 6 neighbors. We're expecting a 7-plet or multiplicity, right? And for the red, we're expecting a. The red had how many neighbors? Just a minute here. Only 2, right? So we're expecting n plus 1 is equal to 3. So we're expecting a triplet. And yes, look at that. So this is a triplet. We can see it. And this is a 7-plet. Okay? All right. So that's pretty abstract. I wouldn't expect you to like that right away. But I do insist that you practice. I've got lots of practice available for you. Let's review then what we can get from NMR spectroscopy. First of all, NMR spectroscopy gives clarity on connectivity, and it does so through location and the size of the signal and also the form or the multiplicity of the signal. All right, go practice.